Hi everyone. I'm going to use this video to explain clogging attack to Diffie Hellman used in IPSec. So first, let me remind or review what Diffie Hellman key exchange involves. Okay, so what computations it would involve. So it's a Diffie Hellman. Okay, so first of all, for all communication parties to use Diffie Hellman key exchange to determine a secret key for a data encryption algorithm, they all need to agree on a set of common parameters. In this case is A and P, where P is a prime number and A is a primitive root P. So this T doesn't look good. That's all right. Okay, so that means we know by Fermat's little theorem, A to the P minus 1 is congruent to 1 mod P. So when A is a primitive root mod P, it means that A to the any m's power mod P is not equal to 1. For any m, of course, it has to be positive and less than or equal to, I'm sorry, less than or equal to P minus 2. Okay, so that is a primitive root. So now the computation involves was a key exchange between Alice and Bob. Are the following. So Alice picks at random SA. So this is a random and private. And private to Alice. So this is a random number. And then Alice, oops. Why do I have this 9 here? Can I? Okay, and then she computes YA, which is A to the XA mod P. Of course, this XA has to be less than, we don't want this to be 1, so this SA has to be less than or equal to P minus 2. Right, so so that goes without saying. Okay, so then this YA will be sent to Bob. So Bob does the same. Bob takes xb. Now again, this is less than or equal to p minus 1. This is random and private to Bob. And then it computes yb, which is a to the xb mod p, and Bob sends it over to Alice. So when Alice gets this yb, so what she does is to compute ka, which is yb to xa's power mod p, because Alice knows xa, Bob doesn't, of course. Nobody else should know xa. By assumption of this protocol. And of course, we also know that from yb or from ya you cannot compute xa, so that's discrete log. So we assume discrete log is difficult, and from yb you cannot compute xb. So that's the underlying assumption. So then Alice computes yb to the xa mod p. So we know that this is equal to a to the xb xa mod p. So then this is equal to a to the xa xb mod p. Likewise, Bob computes kb, which is ya to the xb mod p, and this is equal to a to the xa xb mod p, and this is equal to a to the xa xb mod p. So then, of course, we can see that after this is done, both sides has a common secret key Ka for Alice, Kb for Bob, and they are identical. Then this key can be used for data encryption. And as we see during the network communication, and nobody else, because they know the corresponding private key xa or xb, they won't be able to figure out what ka and kb is. Okay, so this is Diffie-Hellman, but from previous lectures, slides, videos, we know that Diffie-Hellman is vulnerable to man-in-the-middle attack. Okay, so so the idea there is the attacker will just sit in the middle, right? So this is man in the middle attack. So we still have Alice, we still have Bob, okay, but the attacker sits in the middle. So it intercepts Alice. So Alice still has SA, Bob still has SB, attacker now has, so let's call this attacker E, then he has XE, right? So, so this is YA, which is A to the XA mod P, gets intercepted. by attacker. And likewise, YB, which is A to the X B mod P got intercepted by the attacker. Okay, so that means Bob didn't get YA, Alice didn't get YB. So in this time, attacker will compute YE, which is, so this is EA for Alice, which is A to the X E mod P. And also it computes for Bob the same thing, right? So this is YEB, which is A to the XE mod P, and pretends this, so this is from pretends from Alice, and this is a pretense from Bob. Okay, so it winds up that Alice computes KAE and Bob computes KBE, and Eve computes two things. One is KEA, the other one is KEB, and that is equal to KAE, and that is equal to KB. So that's a man-in-the-middle attack. So to counter this attack, of course, we just need to make sure whatever Alice gets from B, supposed to be from B, is indeed from B. So this is authentication. Likewise, Bob needs to do the same. So this is authentication. Okay. However, there is another type of attack called clogging attack. Clogging attack. So what is this? So this is some kind of denial of service attack. So let's say Alice here. Let's say this is attacker. So the attacker will simply send a lot of requests, right? A lot of them. A lot of requests to Alice and ask Alice to compute. So let's say it's Y1, Y2, Y3, Y4, Yn. So the attacker, again, let's call it Eve, picks XE. So Yi, of course, it could be a different, let's say a lot of them. So this will be A to the XEI mod P. And so the Alice by the protocol will need a compute KI, which is YI to the XA mod P. Right, so this is because of this is time consuming, change time consuming, even with fast exponentiation. So this means that Alice needs to, Alice needs to devote CPU powers to these computations. These computations, okay? Of course, you may wonder what happened if I first authenticate all these messages first, and that way you should not receive so many applications, so many requests. But then, of course, authentication is also time consuming, right? So the better way you want to do is you make sure the request is not this type of attack, and then you authenticate this request is from a legitimate user. Okay, so that way, so combining these two, then you counter denial of service attack as well as man-in-the-middle attack. Okay, so now how we can counter this clogging attack? The way is to use cookies. Okay, so a cookie is a number generated at random. Okay, so the idea then is upon receiving a request of computation of yi from whoever, Alice will not, so she won't compute ki right away. And she won't do whatever authentication you may wants to do, because authentication also, verification of a signature also time consuming. So she won't do this. She won't do authentication right away. Instead, she will only do a very simple computation. She sends a cookie to Bob, to whatever, to the sender. Okay, a cookie. And we know in IPsec, this cookie is 64-bit long. And she waits for a response. for a response until a certain set time limit within a certain set time limit. So which is basically, let's say you're using, if you are using TCP protocol, because there is a time limit, the 3 handshake, you have a time limit. But in this case, he's waiting for, so this is time. So what she's waiting for is a response. So this response is from the sender. Including the cookie she sent. So if she doesn't receive this response, then she will not compute KI at all. She will compute KI only when she receives an expected response. Since the attacker doesn't want to be traced, so the attacker will use crafted packet to request YI, so which means that this cookie gets to send to a unresponding IP. So which means that Alice won't receive an expected response in a certain set time limit. Hence, she will not carry out this computation. Okay, so that means that she will not need to spend her CPU power to do unnecessary things, and only when this is done, then of course she can make sure this request comes from a legitimate user that she's engaged communications with. Okay, so that's it. So that's how clogging attacks, how clogging attack is, and how to use a cookie to counter this attack. I'll see you in the next video. I'm seeing you.